Hello, my name is Christopher Coletti. I'm an aerospace and mechanical senior double major at Parks College of Engineering, and I'm going to talk to you about my senior design project. I worked with 3 other aerospace seniors to design and build an RC turbine-powered low radar cross-section aircraft for the Oklahoma State-sponsored Speedfest competition. Per the organizing body of Speedfest, a statement of work was put out requesting an aircraft that was under 9 pounds, used a KingTech K45 turbine, could have a mission endurance of 3 to 5 minutes at wide open throttle, could perform high G maneuvers, could maintain a cruise speed of 130 to 200 miles per hour, and has a minimal radar cross section. So once the statement of work came out, the team sat down and determined what our system and design requirements would be and how that would direct our overall design for the aircraft. Using those requirements, we were able to perform a trade study to analyze what sort of configuration we wanted to meet these requirements. And we determined that a trapezoidal unswept wing with a V-tail and an engine potted above the wing would best complete this configuration and would best meet the requirements that we needed for the competition. So using our general configuration, I sat down with another member and we used an in-house developed code to analyze the aircraft performance and aerodynamics to help us size the wing and the V-tail. As this went on, I also analyzed the stability for the aircraft to make sure that we had all of our surfaces sized correctly to have a stable flight. And through this analysis, we determined that we needed a wingspan of 42 inches with an aspect ratio of 3 and a taper ratio of 0.5. And for the V-tail, it would have a similar taper ratio of around 0.5 and a dihedral angle of 26 degrees. As we went through this analysis, we also worked on doing an analysis for the engine performance to compare that with the manufacturing specifications and incorporate that into our design. So we did a static thrust test to determine that the engine could provide 11 pounds of thrust. We also did a performance analysis to determine the fuel rate for the engine so that we could help size our tank that we would need to have a maintained flight of 3 to 5 minutes. And finally, because we have our engine potted above the wing, we have an engine deck between the V-tails. We wanted to make sure that the thermal exhaust from the engine wouldn't burn away our V-tails. So we did thermal testing using a thermal scanner and a temperature probe to determine where that exhaust cone was and help us size the tail properly to account for that. As we went through the design, we also used open source material to determine how we could build our design with radar cross-section in mind. From a geometry point of view, we determined that we needed to have open edges so that there wouldn't be spots where the radar could bounce around and then scatter as it returns to the source. We wanted to have consistent angles, so the trailing edge and leading edge for both the wing and V-tail were set to be the same angle so we could try and focus the radar to spike in one direction but help lower the radar in all other directions. And that same idea was done when we developed a heptagonal fuselage design to again try and focus that radar in certain directions and minimize the radar in other directions. For material selection, we determined that carbon fiber would reflect radar and fiberglass would allow it to pass through. And so the fuselage was designed using carbon fiber so that we could mask all of our internal components and then also try and hide the thermal exhaust for the engine on our engine deck at the tail. And for the wings, we are using fiberglass so that the radar would pass through and help minimize the cross-section as seen by the radar. Once we had our design and our material selection process completed, we moved forward with manufacture. For the fuselage, it was manufactured using a plug-in mold so that we could make multiple bodies, and it has a top and bottom composite structure that's married together using carbon fiber strips on the inner seam. The wings were cut out from foam using a CNC, and then a plywood spar with fiberglass made an I-beam along the length of the quarter cord and 3/4 cord for the wing and along the center of the V-tail to help strengthen it before it was wrapped in fiberglass. And once we had our fuselage and wing and tail built, everything was assembled together and you can see our completed aircraft. So at competition, we went and competed and found that during our taxi tests under the high crosswind, there was a force that was acting on the nose because it's such a long fuselage that whenever we went up to a high speed during the taxi test, the aircraft would spin around, and the tail did not have enough vertical volume to be able to counteract that force. So unfortunately, we never got off the ground and didn't get to fly at competition. But we got a lot of valuable experience while there. We had a great time talking with the other teams and with the governing body, and got a lot of feedback, so we are currently working on helping develop the program at Parks College so that future teams will be able to compete at this competition. I had a great experience over this entire year working on my senior design and gained a lot of valuable experience both in manufacturing and analysis for this sort of aircraft. So I want to thank you for your time for listening to this video, and I hope you enjoyed it. Thank you.